recording quality is a little suspect. I recorded the presentation for, I think it was my Thursday class. That was the YouTube video I tried to start off playing. So we'll just pick up here. But if you do want to sort of see the whole presentation, I've captured on the screen what I was writing down here. That other screen capture or lecture capture that I started to play is the one, and it should be obvious on the YouTube channel which one it is. I've been using this for a while in teaching. The interview was done back in like 2008. So I probably heard it in 2009 or something like that. But so I talked to some of my colleagues here, the people that teach micro, just to see how far out there this is. And actually this hygiene hypothesis is an important line of thought in immunology circles. Basically, the idea is that the human condition, which has been adapting to its environment for hundreds of thousands of years, or 100,000 years or thereabouts, maybe, well, I guess more, has fine-tuned immune function to the types of organisms out there that we deal with on a regular basis. And so in the past 100 years or so, we've started to become more sanitary, which has led to a lot of important advancements, like post-Reconstruction South was economically non-existent almost because of stuff like this. And as soon as the outhouse was introduced, a lot of things changed. It's not the only thing, but that's kind of the point that they're making in there. But perhaps we've gone a little bit too far. Are we too sanitary? Are we letting our immune systems try to deal with an internal environment that they're not prepared for? If these attack cells, which we're going to talk about later, are left to their own devices, are they going to start attacking things in our body that they're supposed to leave alone? And so the suggestion here is that the parasitic infestation stimulates what they're referring to as lullaby cells, and I'll explain what those are later on, which will then counteract the attack cells so that they don't get carried away. And it seems to be a reasonable hypothesis, and it does have some predictive value. Probably a couple of years ago, I can't remember exactly which semester it was, but after doing this in class, playing this in class for my students, one of my students came up to me and shared a story with me which really kind of illustrated what was going on here. I never really had a chance to consider this so much. She grew up in Mexico City. She never really explained the ins and outs of her life, why she was in Mexico City. I kind of painted in a little bit of a backstory for her, which I don't know is at all true, but the way I see it, her parents were in the Foreign Service, worked for the embassy or something like that in Mexico City. I have no idea whether that's actually true, but that's the story that I've made in my head. Because I believe she told me when she was 19, she came to the United States for college, and I think she said she came to DC. And so going to DC just made me think of her parents must have been in the government or something like that. And when she was in her first year at college, she was convinced that her new friends at college were poking some fun at her, trying to convince her that one of them had this debilitating allergic reaction during, spring season when allergy seasons came around. Because she had never, ever met anybody that had allergies all the time she was growing up in Mexico City. It suggests that, even something geographically, kind of right next door to us, like Mexico, might have a situation where the hygiene hypothesis is kind of put to the test a little bit. You've probably heard somebody say, if you're going to visit Mexico, don't drink the water, or something like that. And whenever I've heard that, I've thought, well, if you're not supposed to drink the water, it's probably not very good. What do the people living there drink? But of course, they're going to drink the water. They're going to potentially do some things to treat it a little bit, I'm sure. But they're adapted to that environment. So they might have been exposed to things that'll make tourists very sick if they drink the water, but their immune system has adapted to it to some degree. And that might actually be what is at the root of the story that I heard from my student, that she didn't know of anybody with allergies, because maybe in that kind of environment, there is this sort of low-grade infection of whatever it might be. I don't know necessarily that it's a waterborne pathogen, but it could be something like that. And it just makes it so that those sorts of conditions are unheard of. And it's something to really think about, that we're always kind of thinking about the immune system, and it's largely how it's explained through the textbook and what I'm going to cover tonight, about this idea of attack cells, things going out there to fight off infections. But left to its own devices, that can really get out of control and cause sort of these sorts of problems. So anyway, so I just wanted to wrap up the podcast there. So now this week is specifically about the immune system. It's still the same chapter, but we're going to get into talking about sort of these things that are going on a little bit. So last time, what we covered was basically in this first section here about the lymphatic system. And then the rest of the chapter is really about the immune system. In the first half, I'm going to talk about the innate immune system, or innate immune responses, which is the next section. In fact, the section that's up here that's titled Barrier Defenses in the Innate Immune Response. And then after that, we're going to look at the adaptive immunity, concentrating on the T and B lymphocytes as the basis for that. The amount of time that we have in one night is just not enough to do this chapter service. It used to be that I did the entire chapter in one night. Just last semester I was doing it that way. And this semester I decided to break it up so that we had more time. So we did the lymphatic last week, and this week we're just concentrating on the immune system. But it's still not really enough time to do everything. So I am going to necessarily be a little brief about some things. So the first thing I want to kind of talk about is this idea of barriers. There's essentially five barriers to consider. And separating up into five things just talks about the different organ systems that they're part of. But really, there's one continuous barrier. What particular tissue lines that barrier varies depending on where we're looking. But what we're talking about here is the skin, which is pretty obviously the barrier between us and the outside world. But then where the skin kind of gives way to open cavities, like our nasal cavity or our oral cavity or something like that, there's a different barrier once we pass over from the outside where we have the skin over our lips to the inside where we have a different lining for the digestive tract. So the skin, obviously, is the cutaneous membrane. That's the definition of it. And then the other linings that we're talking about collectively are the mucosal membranes that we have in our systems. So there's the respiratory mucosa, the digestive mucosa, the urinary mucosa, and the reproductive mucosa. All of those are potentially open to the outside world, whether it's the opening to the nasal cavity or opening to the oral cavity or the opening at the anus or the urethral openings or whichever opening might apply to your particular reproductive tract. Anything that might get into any of those tracts is still immunologically considered outside of our body, just like anything beyond our skin. Things have to cross over through those barriers to be able to cause infection. And those barriers, the skin and all the mucous linings, do have some components that actively inhibit microbial growth. In your skin, the secretions have a slightly acidic pH. Your skin actually has a pH of about 6.5 compared to the 7.35 inside your body. So that bacteria that want to get inside your body and live at 7.35 are inhibited by that pH outside your body. Now, there are bacteria and other microbes that are able to survive in that whole range of pH, so the pH of your skin isn't necessarily going to inhibit their growth. But most bacteria that might want to get into our body won't want to live in an acidic environment like in our skin. Some of the other secretions, I think, is it tears or I can't remember, there's a few other secretions that are slightly acidic too for the same reason, to inhibit microbial growth. Tears and mucus and saliva have antimicrobial agents in them in the form of enzymes. So there's something called lysozyme, which is found in tears, and then there are enzymes in your saliva, which are part of digesting food also. And those sorts of things, which will actively break down the molecules that make up the outer covering of microbes, and that can inhibit bacterial growth too. So there's a number of different things that can happen. I just pulled this picture up. I just did a Google search for immunological barrier, and this is out of some other textbook. I don't know offhand which. I just did this, immune barriers, not immunological barriers. I just did a Google search for that, and I pulled up that picture for it. In the book, the picture they have a kind of addresses that isn't addressing all of those specific barriers in the picture, but rather obviously highlighting the nasal and oral cavities and giving some examples of some of the components of that that help act as barriers. So there are some immunological cells that are present, as well as enzymes and other chemicals that can be secreted to help inhibit growth there. This table just runs through a few of the components of those barriers that play a role. Skin as its physical structure, and then skin as its secretions, secretions from the oral cavity, namely the saliva. The stomach obviously is a great place to inhibit bacterial growth because of its very acidic environment, but then also it has digestive enzymes in it that would break down anything that you happen to swallow. And then some things from the mucosal surfaces. So a number of things that play a role there. The last one in the table there, it says normal flora. Now, flora, you might recognize the name like in a floral shop. We usually use it to refer to plant matter, but here it's used to describe bacteria. So we have some normal flora. We have bacteria that live in our body and on our body on a regular basis. And we've adapted and co-evolved with them so that we are a symbiotic set of organisms. They want their environment to be left unchanged. They want us to be normal and healthy because that's going to help them be normal and healthy too. So they do some things to actively inhibit growth of other bacteria that might cause problems and that sort of thing. So they do play a role with that. And that's sort of what's mentioned down here. Then in the innate immune response, there are a couple of types of cells that play a role in actively going out and hunting down and destroying or attacking, if you want to call it that, although that's not exactly what they meant by attack cells in the podcast. But still has that kind of military metaphor feel to it. One of those types of cells are called phagocytes or phagocytes. Phago means to eat. It's the root of the word esophagus, just to relate it to something else that has to do with eating. And there are two types of cells mainly that fall into that group. They're both white blood cells. Now, there are actually 5 types of white blood cells. Did I share with you the mnemonic of never let monkeys eat bananas? It's not funny. Okay. Easy way to remember the 5 types of white blood cells is the mnemonic never let monkeys eat bananas. The N in never stands for neutrophil. The L in let stands for lymphocyte. The M for monkey stands for monocyte. And then E and B are eosinophil and basophil. That order, that sentence there actually tells you the 5 also in their decreasing order of number. The most common type of white blood cell is the neutrophil. It makes up about 2/3 of the white blood cells in your body. The next most common one is a lymphocyte, which makes up about 20 to 25% of the white blood cells. And then come monocytes, which makes up a little less than 10%. So right there, we're talking about 95+% of the white blood cells in your system. And because of that, I'm just going to leave off the eosinophils and basophils for now. Now, lymphocytes are the ones that are important for the adaptive immune response. We're going to talk about those in the second half tonight. Neutrophils and monocytes are the ones that become phagocytes. Neutrophils are called neutrophils all the time. When they're activated, they're phagocytic, but they're still called neutrophils. Monocytes, when they're inactive, we call them monocytes, and when they're active, we call them macrophages. And macrophage just means big eater, essentially. So these are big cells that go around gobbling up cellular debris and pathogens and whatever might be out there. Neutrophils outnumber monocytes and therefore macrophages quite a bit. So generally speaking, if we see a phagocytic cell, it's most likely going to be a neutrophil. But some places where phagocytic cells are common, it's actually macrophages that are there. Like in the spleen, there are macrophages that help digest down expired red blood cells. Something similar in the liver, also macrophages. Wandering around deep in at the end of your respiratory tract, there are macrophages that help gobble up any airborne pathogens or debris that might make it all the way down into your lungs. So macrophages are kind of the usual example of dedicated phagocytes, and neutrophils are there to respond to infection and become phagocytic when called upon. So most often, if you see a phagocytic cell, it's going to be a neutrophil, just in a random sample, if you will. But macrophages are found in very specific places, and they're usually dedicated phagocytic cells in particular places, like the lungs, and the kidney and the spleen, liver and the spleen, and that sort of thing. Now, in the paragraphs underneath this, the first paragraph, it's just sort of a setup thing. The second paragraph, the second word is bold-faced, and that's macrophage. And then in the third paragraph, the second word is bold-faced, and that's neutrophil. Then there's a little sentence at the end, sort of a final mini paragraph there, and the second word is bold-faced there, and that's monocyte. Monocytes are just the white blood cells that become macrophages after they're activated. That's all that's mentioned there. Now, the point of a phagocyte is that it goes out and eats or ingests things in our internal environment. There's this really nice little video that I want to share with you that sort of shows this process happening. Now, the video is actually on Blackboard. I have a number of videos that you're welcome to look at. They're sort of placed in order based on the topics that we go through. So probably about halfway down the page, there's a series of videos that I've grabbed for the immune system. And so there's this one here. There's no sound to this. All we're going to see is this video captured in what I assume is a petri dish, where we have a number of what must be red blood cells floating around, so to speak. And then this is a phagocyte, a neutrophil, that's crawling along in this petri dish, chasing down a bacterium, which is this thing that we see right here. Now, there's no audio to this. I'll just play it off. I always feel like there should be a little player piano going with this, like a silent movie. But I'm going to show you another video later on, which is a really good representation and a much more recent video of a cell moving kind of like this. But this is how white blood cells move. And then there, it finally reached out and grabbed the bacterium and pulled it inside the cell. Once it's inside the cell, it's in a little vesicle, and that vesicle merges with an organelle called a lysosome. The lysosome is essentially the stomach for the cell. It has an acidic pH, and it has digestive enzymes. And so when it merges with the vesicle that contains the microbe, it digests the microbe. And then the fragments of the microbe are left to be disposed of. When you have a rather severe infection, you're going to have a bunch of these cells going around gobbling up all of the microbes that are causing the infection. And they might accumulate so many microbes that are in some state of digestion that it eventually kind of kills off the white blood cell. And when you see an accumulation of those white blood cells that are dying off at a site of infection, that accumulation is what we call pus, okay, which is largely those white blood cells. So that's a pretty good representation of what the white blood cell does. I like the little video play of that. In the book, they don't actually have a depiction of that process, sort of the steps of it right here. There is a picture later on that has to do with something else that shows what's happening in the cell to digest things. And I'll show you that when we get to that part of tonight's material. The other type of cell that's part of the innate system is called a natural killer cell, or sometimes just referred to as an NK cell. An NK cell is actually a lymphocyte, but it's different from the kind of lymphocytes that we're going to concentrate on for adaptive immunity, in that it's a non-specific cell. So phagocytes, which we just looked at, and natural killer cells, what makes them innate immune response cells is that they're not being specific. They're just going after whatever might be in our body that can be infectious. I'm not going to scroll down on the page right here, but the next thing after it talks about natural killer cells, it talks about how these types of cells can recognize foreign invaders, so to speak. And it talks about pattern recognition, or something like that. A bacterium is a single-celled, very, very simple, very, very small pathogen. And it's usually at the mercy, so to speak, of its environment. Bacteria, especially the ones that tend to infect animals like us, don't tend to be motile. They don't have some sort of mechanism to swim around. If they do, it's a pretty rudimentary one. More often, they're at the whim of the movement of whatever fluid they happen to exist in. Okay. To help them stay located or stay anchored where they want to be, they'll tend to have carbohydrates attached to their cell membrane or cell wall, depending on the type of microbe we're talking about. Now, if we covered you with carbohydrates, what would happen? What's a more common name for carbohydrate? Yeah, say it, Monique. Say it, you said it right.
Sugar.
Sugar, right. Okay, so let's take Monique and cover her in sugar. Okay, what's going to happen? Yes. We'll assume we're doing it in a clean room.
We're gonna feed them. I don't know.
No, we're in a clean room. There's nothing I'm going to feed off you, don't worry. But when you're covered in sugar, what can you expect to have happen? It won't be some extreme to poor girl or Monique. But let's just say you were eating cotton candy. Okay? What's happened to your fingers when you're done eating the cotton candy? They're sticky, right? The carbohydrates that are on the outside of bacteria help them stick to things in their environment. The extreme hydrophilic nature of carbohydrates makes them very reactive at the hydrogen bond level, and they can stick places. That's very unlike cells that are in our body. The cells in our body might have the occasional carbohydrate on its surface, but not anything like you'd find on the outside of a bacterium. So phagocytes can recognize these as being foreign invaders because they don't look like cells that are supposed to be in our body. Okay. Now, I said specifically phagocytes for that because natural killer cells don't really get involved with bacteria. Okay, so here's the recognition thing down here. Natural killer cells are more aimed at taking out cells that are about their own size. So the neutrophil we just watched, it was obviously picking on a cell that's much smaller than it. But natural killer cells usually go for full-size cells, which might be cells in your body that are infected by something. They might be cancerous cells. They might be cells that just aren't behaving properly like they're supposed to. What natural killer cells usually do is they release chemicals that will kill the cell. And some of the bold-faced terms in that section right under natural killer cells are mentioning a couple of the chemicals that play a role in that. Okay, and they're actually going to come up again when we talk about some of the other more specific lymphocytes and how they do their job. So I'll leave that for that. But these cells, natural killer cells and phagocytes, are part of the innate immune response in that they're going to react to anything that might be causing disease or damage in our body and try to get rid of it. Okay. Phagocytes are usually aimed at pathogens like bacteria or something like that, and natural killer cells are usually aimed at larger cells that might be infected body cells or diseased body cells or something like that. And here's the thing about the pattern recognition stuff. Besides cells, there are also some chemicals that play a role in the innate immune response. So soluble mediators of innate immune response just means chemicals that are part of this, chemicals being soluble. Cytokines and chemokines are classes of hormone-like molecules. White blood cells will kind of interact with each other, talk with each other, if you will, using these. So it's sort of the hormone-based communication within the immune system. Early induced proteins are proteins that cells make when something bad happens to them. One class of those types of early induced proteins are called interferons. There are 3 or 4 different types of interferons. I can't remember, I think it's 3. There's an alpha interferon, a beta interferon, a gamma interferon. There might be a delta interferon, but I can't remember. I want to talk about one of those a little bit. One of those interferons, which I think is gamma interferon, is an early induced protein released by cells that have been infected by a virus. So let's say you've been exposed to the influenza virus and you're going to get the flu. That influenza virus is going to infect cells lining your respiratory tract. Okay? And the way that viruses work, their outer coat, the protein structures on the outside of the virus, mimic some sort of molecule that can bind to that cell. Okay? Now, it's not what I'm about to give an example, but just an example that you might be, you can imagine being familiar with. But this is not at all the real way it works. Let's pretend that the outer surface of the virus has some shape to it that looks like glucose. And what it'll do is bind to the glucose receptor transporter that's on the outside of every cell that helps to pull glucose in. This is not actually the way the virus works, but let's pretend. And so by binding to the glucose receptor, pretending to be glucose, it's going to stimulate that cell to pull the virus inside. And then once it's inside the cell, it can take over the cell's molecular biology equipment. It can make copies of its own genetic material and use those genes to make new virus particles. Okay? Something like that. More often, viruses don't work by getting internalized into the cell, but rather by injecting their genetic information into the cell. But whatever it is, the genes get into the cell and direct that cell to make new viruses. When a cell in our body gets some sort of foreign DNA, and there's a molecular marker to our DNA that foreign DNA isn't going to have. So when foreign DNA gets into any of our cells, they automatically start making this molecule interferon, and they start releasing it. And again, I'm pretty sure it's gamma interferon, but I might be mistaken. The interferon molecule is then released from the infected cell, and it binds to receptors on neighboring cells, which hopefully haven't been infected by the virus yet. And so the interferon tells that cell, there's viruses in the neighborhood, they're going to infect you. Shut down. Okay. What the virus needs to replicate is the cell's protein synthesis machinery. And if the cell, when it gets the interferon signal, shuts down its ability to make proteins, then the virus can't reproduce. Okay. It's a great way to get rid of the virus, but it's lethal to the cell. Okay. But that's okay. Okay. It's better for the cell to die not allowing the virus to reproduce than for the cell to die because the virus reproduced. And this is an epithelium. Dead cells are going to be replaced just fine after the infection's gone away. So that's an example of an early induced protein. Okay, interferon is an example. There are other early induced proteins that are induced for different reasons. Some of them have to do with cell damage. Some of them have to do with infections, like that, et cetera, et cetera. There's a number of different things that can happen. And then, and actually in here, they're not talking about that virus example I just gave you, but I wanted to illustrate the idea of early induced protein a little bit. The next type of chemical to be related to this, to be part of the innate response, is complement. And I've opened this figure up here. Okay. Now, there are two words that are pronounced complement in English language. One, which is what we're talking about here, is spelled C-O-M-P-L-E-M-E-N-T. The other one is spelled C-O-M-P-L-I-M-E-N-T. Complement with the I is my, you look beautiful today, that kind of thing. That's a compliment. Complement with an E is referring to things that work together. Okay, so when you say, you know, a husband and a wife complement each other, they work together very well, that's what you're talking about. You're using the word complement with an E, not complement with an I. The complement protein system is a system of proteins that work together, I guess you could say, with other aspects of the immune system to kill off cellular pathogens, namely bacteria. In this figure, starting up here and going all the way down, we have a number of molecules highlighted that are indicated by a code that says C and a number. Okay. The C stands for complement, and the number is the number of the protein in the system. There's C1, C2, C3, C4, et cetera, all the way through C9. Those are the complement proteins. Now, I'm actually going to work backwards through this picture just to explain what's going on. The point of complement is that it forms a channel called the membrane attack complex in the surface of a cellular pathogen, like a bacteria. In this picture, this one here that kind of looks like, I don't know, it kind of looks like a Mardi Gras cake to me or something like that. But this is actually way out of scale for the pathogen here. All of these other things that are sticking out of it are supposed to represent other membrane attack complexes. This one's just been enlarged for the sake of the drawing. They are channels. They make holes in the cells, and the inside of the cell spills out, and the cell dies. It's a rather messy way to kill a cell, but it does destroy the cell, and it's not able to cause an infection. The membrane attack complex is composed of a number of different proteins, but it includes C9, C8, C7, and C6, which join together with C5 to form this thing. And actually not all of C5, but a fragment of C5. That fragment of C5 is what's referred to as C5a. There's also C5b, which is just to say that the overall C5 protein breaks into two pieces. One piece helps form the membrane attack complex. The other piece isn't part of this. Okay. C5 is digested or broken into two pieces by C3b, which obviously is half of the C3 complement protein. So there's C3b here and C3a here. They're both parts of C3. C3b breaks down C5, and C5a then makes the membrane attack complex. C3a, in this picture, they're depicting it as being attractive to phagocytes. It attracts phagocytes to the site of infection so that they can eat up all of the remnants of the killed off pathogens. Okay. Now, the way that this happens is a little bit more complex than what's suggested in this picture, and just a little bit more complex. What happens actually is that C3a activates what are called mast cells, and I'll show you those a little later on. Mast cells then set up the inflammatory response. And part of the inflammatory response is going to be signaling macrophages and phagocytes to go to a site of infection. And then a fragment of C3 actually helps the phagocytes to find, locate, whatever you want to say, and destroy the pathogens. Okay, so they play a part there. So it's a little bit more than they just attract phagocytes. They actually stimulate the inflammatory response. C3a stimulates the inflammatory response through mast cells, and with that, phagocytes come along, and then they interact with the complement proteins, and they find their targets and destroy them. Now, from C3 down through the end of this, what I've described so far is sort of the basic or common complement pathway. Okay. There's actually two ways to get to that point in this picture. The one that's shown in the picture, this one here that includes C1, C2, and C4, is called the classical complement pathway. And then the other way to get here is to kind of directly go to breaking down C3, and that's called the alternate complement pathway. The reason that's an important distinction to make is that is that the classical pathway requires antibodies. The alternate pathway is non-specific, meaning that it doesn't require pathway antibodies. So, when we're talking about just the innate immune response, we're talking about general responses, non-specific responses. And so really for the strict innate response aspect of complement, we're talking about the alternate pathway. The classical pathway is going to tie into adaptive immunity in that it requires antibodies to be present. So let me go back to this picture again. C3 is broken down by what's called C3 convertase. And C3 convertase is made up of two pieces which are colored separately because they are half of C2 and half of C4 put together. C2 and C4 are broken down because they interact with C1, which is more than just this little green thing. It's sort of this whole thing at C1. Its job is to simulate the breakdown of C2 and C2 and C4, which then generates C3 convertase and gets us into the whole common pathway that ends with the membrane attack complex. C1 is activated when it interacts with antibodies that are bound to the surface of a pathogen. Okay. So what's going on right up here, we have not gotten to talking about what that is because this is part of the adaptive immune response, which we're going to talk about later on tonight. But that's what's actually going to start the classical pathway, which was the initial description of what complement was. And then it was discovered later on that there's a non-specific version that goes right into breaking down C3, which is not actually depicted in this picture, but it is the case. Oops, let me get back here. So that's complement. The last part of what this part of the chapter talks about is the inflammatory response. And so to introduce the inflammatory response, I want to go to this picture here. This is a picture that I've used for a long time to describe the inflammatory response. I think it's a very good depiction of the idea. It isn't the inflammatory response. We'll talk about how that occurs in a second. But I actually am aware of this picture originally because when I was in graduate school, one of my roommates was a medical student. And in his physiology class, this was the picture that the professor put up on the screen to talk about this. Inflammation is really the accumulation of fluid at a site of injury or infection. It's based on an increase in perfusion to that tissue. When I say perfusion, I mean blood flow to the tissue. What initiates inflammation is basically going to dilate blood vessels in the area so that more blood flows to the affected tissue when an infection or injury needs to be addressed. Okay. Along with dilating the blood vessels, what's also going to happen is the intercellular clefts, where the simple squamous epithelial cells come together in the wall of the blood vessel. They get a little leakier, so more stuff can come out of the blood into the surrounding tissue. The basis of that, what's the center column in this picture, is swelling. Okay? As there's more perfusion to tissue, more blood going through the tissue, that means that more water is going to come out of the blood and get into the tissue, which is going to cause it to swell. So when we started talking about the lymphatic system, that's sort of where I started. Okay? At capillary exchange, there's an unequal balance between filtration out of the blood and reabsorption back into the blood. So water accumulates in the tissues. If you increase the blood flow to a tissue, that just means that more water is going to come out of the blood, and that's going to cause swelling. That swelling, of course, is going to go down as the fluid moves from that tissue and into the lymphatic system. And so, again, that plays into the lymphatic system being an important part of the immune response. Now, on either side of our swollen pillar in the center here, we have sort of the consequences of that increased perfusion, and they're sort of slightly unrelated consequences. So on this side, the next column over is labeled redness. So the pillar has lost his toga and he's embarrassed because his fig leaf is showing off. And we know that he's embarrassed because his face is red. When you're embarrassed and your face turns red, what's happening is increased perfusion to the skin of your face. It's just part of that emotional response. But it's the exact same idea. It's an increase in blood flow to the tissue. And so when there's more blood flowing to a tissue, the tissue is going to necessarily get to be red, okay? Because there's going to be more red blood cells, more of that red pigment there. Depending on how much increased perfusion there is and necessarily where in the body it's happening, you may or may not see the redness. Okay? If it's a very small localized event, there might not be enough volume of blood increased there to actually see redness, but there is going to be an increase in blood flow there. And then the last pillar on this side is labeled heat. In the cartoon, it's depicted because it's being lit on fire by the embarrassed guy's torch, which is just a good way for medical students to remember that that's heat. But really, it has nothing to do with a torch or anything like that necessarily. All it is when blood flows to a tissue, it's going to make that tissue warmer. So if you've been embarrassed, you know it because your face feels warm. Okay? It's just, it goes hand in hand with an increase in blood flow. Now, there are other things that can increase heat with the inflammatory response. There are chemicals that are released by damaged or diseased tissue, which will actually increase temperature in that tissue. Collectively, those are called pyrogens. Pyro as in pyromaniac, referring to fire. So pyrogens generate a pyro response, so to speak. That's going to help if you have an infection because just like the bacteria that want to get into our body are looking for a particular pH, they're also looking for a particular temperature environment. So anything above 37 degrees Celsius is likely to inhibit bacterial growth. So at a site of local infection, the tissue might increase its heat generation, which can hopefully kill off some of the bacteria. When the infection gets to be systemic, then that kind of thing, the increase in heat, we call the fever. Now, the problem with a fever is if it's not effective right away, if it doesn't get rid of the bacteria and the fever persists, the higher temperatures you run as you're getting closer to 42 degrees Celsius for longer, then you're going to start damaging your own tissue because the cells in your body would also like to live at 37 degrees Celsius. So if your internal environment is off from that for too long, then you're going to start causing damage to your own tissue. And oftentimes with the prolonged elevated fever, it's the central nervous system tissue that's at most risk. But back to the idea of local inflammation, whether it's the increased perfusion or chemical signals, there can be an increase in heat there too. It does depend on exactly what's going on, how much heat might increase. If there's not a microbial infection present, like if you've sprained your ankle or something like that, there might be a little increase in heat because of more blood going to that area, but you're not going to have pyrogens increasing temperature because there's nothing to fight off. So how much heat changes kind of depends on the situation. The other side over here, we get into pain, which can simply be because of that swelling. Just as the tissue accumulates fluid, there's going to be pressure put on different structures. And if some of those structures are nerve endings, then that might result in pain sensations. But more likely, the pain that we associate with inflammation is a chemical signal. So when tissue is damaged, or it's under threat by infection or something like that sometimes, it'll release chemical signals that will actually activate pain receptors. I talked about this, I think, a little bit back when we were talking about hormones. I talked about aspirin and Vioxx and that sort of thing. Prostaglandins are a type of molecule that's released during inflammation, which will actually activate pain fibers. And taking a cyclooxygenase inhibitor like aspirin or Vioxx will inhibit that enzyme, and you won't make prostaglandins, and the pain will go away. The point of having pain here is basically as a behavioral signal. Okay? Pain doesn't do anything to get rid of the infection or help heal the tissue directly. Rather, it tells you at a conscious level that there's something going on. So if you sprain your ankle, it hurts to put weight on that ankle because of pain fibers that are activated there. And so you favor the other foot more and allow the sprained ankle time to heal. Okay? Or you might put your foot up altogether or something like that. It's a behavioral cue to get you to change what you're doing to help with healing. Okay? The last one there is loss of function, which is kind of related to that, especially with the sprained ankle idea. As swelling takes place, as fluid accumulates in the tissue, it's going to make it harder for the tissue to do its job. So if your ankle is swollen because you've sprained it, then it's going to be harder to move your ankle through its normal range of motion. That's loss of function. Pretty good example. Now, you're going to see loss of function elsewhere. So like if you have arthritis, you have swelling in joints, it's going to be harder to move those joints. If you have pancreatitis, swelling in your pancreas, the pancreas probably isn't going to secrete digestive enzymes quite as well as it normally would. So wherever it might be, wherever there's some inflammation, you're going to see loss of function. Okay. Now, I use the sprained ankle example because it's probably something that people can get sort of wrap their minds around really easily. But I also use it because I have a pretty, I think, profound and personal example to share with that. When I was younger, and for those of you that had me for AMP1, when I was about 15, I was in a moped accident, and I broke my tibia and fibula as well as my scapula and a few ribs. Sound familiar? Okay. That's a case study from one of the AMP1 tests. But, so I broke my leg. It didn't heal back correctly because I have this heart condition, and so I couldn't go into surgery, because I was at risk for bacterial endocarditis, again, part of that case. So when I was about, I want to say 26, but that doesn't sound quite right. I must have been a little bit older. I had surgery to correct the broken bones because they healed at an angle, about 10-degree angle. So they were sort of rebroken and surgically put back together. And they put a rod through the tibia, and so they had to put a screw at the ankle and a screw at the top to hold that rod in place. And now I can't really move this ankle very far. This ankle very far. Compared to my other foot, which is fine, that's about as much as I can plantar flex this ankle. That's because this ankle is going to always be in an inflammatory state. Okay? I can feel around that ankle that there's a little bit of swelling there. It's never going to go away because the tissue's just sort of always been altered. There's scar tissue there. There's irritation when I walk, and it's just always going to be going to have a little bit of inflammation in there. More impressively, maybe, I can move this ankle pretty far over to the side. I can't move this ankle nearly as much. Okay? There's just a lot of loss of the range of motion, the function of that ankle because of the inflammatory response that followed the surgery that was there to fix my leg. Okay, so these sorts of things happen. I really should have had really good PT after the surgery, but for whatever reason, my surgeon didn't write orders for it, or my HMO didn't cover it. I don't know what it was, but I didn't have very good PT afterwards. So I'll never get full range of motion in that ankle back. And that's just because the inflammatory response is going to happen in a situation like that. Now, the picture from the book that addresses the inflammatory response is really just indicating what kind of stuff happens at the site of damage and infection. So here we have the skin that's been cut through. So the little wavy line that we see right here represents the transition from the epidermis to the dermis. So the cut has gone all the way through the epidermis and it's down into the dermal space there. So bacteria from the outside can get in through that because now this barrier is completely breached and it's no good right here. So the pathogens can get in. When that happens, the damaged tissue is going to start to release some signals which will initiate the inflammatory response. Some of what's being released from here are going to be pain-activating chemicals, and some of them are going to be chemicals that will activate mast cells, which are what these two purple things here represent. Mast cells then go on to release histamine. Histamine will directly cause vasodilation and the opening of intercellular clefts, not completely opening it up, but making the blood vessel a little leakier. Now, because of that, there's going to be more fluid flowing to this area, and it's going to cause swelling, which we see right there. And the white blood cells that are in the bloodstream here can move out into the tissue and become phagocytic. And here we see one that's actually engulfing one of the pathogens that comes in. Now, I'm going to zoom in for a second on these white blood cells because white blood cells have very peculiar nuclei. In the two cells that we're looking at here, the nuclei are not just your basic spherical organelle in the middle of the cell. With white blood cells, they tend to be lobular, which is to say there's usually chunks of nuclear material linked together by thin little nuclear bridges. And this one down here is a little bit better example of that. So here we have a chunk which has DNA in it, and then a little thin bridge that connects to another chunk that has DNA in it, and a thin bridge that connects to a bigger chunk here that has more. When these cells are going to squeeze out between the endothelial cells into the surrounding tissue, it's a lot easier for them to do that if they can push a little bit of their nucleus through at a time, rather than trying to squeeze this big spherical nucleus all at once. And so that's going to make it possible for cells like this to migrate out into the surrounding tissue and become phagocytic. I didn't really notice that they apparently just copied this cell and pasted it there, but really the cell should leave the bloodstream and move into the surrounding tissue. And they can do that because they can kind of squeeze through the cracks in the cells. You've probably seen, because they're all over the internet, pictures of cats crawling into weird little box type spaces. And so think of that cat trying to get in through that little hole that's still a box of some sort. That's what the white blood cells are doing. They're just sort of squeezing through this very small opening to get to the other side. And they can squeeze their nucleus through because it's already kind of broken up into small pieces that can be shoved through a little bit at a time to get out into the cell. So rather than kind of describing what the inflammatory response is in this picture, this is just an example of it occurring at a particular site of injury and infection. Okay. In the text after this, they talk a little bit more about what's going on. They talk about tissue injury, vasodilation, vascular permeability, and phagocytes being recruited and moving out into the surrounding tissue. So it addresses those things there. And then after that, we hit the end of the chapter. So that kind of hits all the major points in the innate response. Now, normally I want to take a break at about 10 till. But this is a good stopping point. So I'm going to take a break now, and we'll just go ahead and take our 20-minute break now and come back in at straight up 7 o'clock by that clock, and we'll finish up the other stuff. And at least having that extra 10 minutes makes it a little bit more comfortable to cover the stuff I have to in the second half. So, see everybody in about 20 minutes.